Hi guys, welcome back. We're still talking about CFD, and now we're going to talk a little bit today about DNS, direct numeric simulation. So what is the DNS approach? The DNS approach is let's use CFD to resolve all of the scales that we talked about last time, from the largest scale to the Kolmogorov scale. What is the computational requirement? To do that, what would it look like in a CFD situation? So we're introducing fluid dynamics in this context. We're going to estimate the computational requirement as a function of Reynolds number, and I'm going to apply it to an example, the backward-facing step, which is a canonical problem in and of itself. And then we're going to look at what it would be like for a more interesting problem like flow over an airplane or even pipe flow. All right, so remember when we do CFD, we discretized our governing equation, something like that, and we applied it to a grid, so in IJ space or XY space. And the problem that we're going to talk about today is flow over a backward-facing step. So the flow is coming this way and spilling over. This is going to be completely filled, so you have a vortex that forms here, and the flow will go through the domain like that. All right. So using a finite difference approach, we would discretize each derivative and apply it to a domain. And here's an example of what the solution might look like. So you get this secondary flow that forms just like we saw in the lid-driven cavity flow. So what spatial resolution is required to resolve the turbulent flow all the way down to the Kolmogorov scale, right? And that's all the physics that's going on as far as the continuum fluid mechanics is concerned. So let's take a look at what that requirement would be. So let's imagine that we want to use a spatial resolution down to the Kolmogorov scale. That's how fine we would have to resolve the mesh, right? And let's say that in general, that the number of nodes that we would need then are something like 10 times the characteristic length scale. So if we're doing flow over a step, you can't just, and the step has a characteristic length of L, you can't just have the domain that big. You got to have maybe a little bit, maybe 5L upstream and 5L downstream in order to get a good representation of what that flow field would look like. So let's say that the domain in general has to be about as large as 10 times the largest imposed scale length. And you're going to resolve that with a delta x, and we'll say that delta x is the Kolmogorov length scale, eta. So this is the number of nodes we would need. I can then plug in what I know the Kolmogorov length scale is with regard to the dimensional analysis that we did. And I can also resolve what this turbulent dissipation rate is in terms of some characteristic velocity and the length scale. And when I collect these scales together, I see that it's 10 times the Reynolds number raised to the 3/4 power. So that's pretty cool. It says that the number of nodes that I'm going to need in a simulation to resolve from the largest scale to the Kolmogorov scale scales like Reynolds number to the 3/4 power times 10. Now, that's in one dimension. If this is a two-dimensional or a three-dimensional flow, I've got to cube this. Turbulence is fundamentally a time-dependent three-dimensional flow field, so I would cube it to get the spatial requirement that it's actually 10 to the third times Reynolds number to the 9/4 power. That's how the 3D simulation scales. How many steps m are we going to need to take in time? So this is a time step. So again, we're kind of beholden to the period of that smallest eddy. In order to resolve that period, in order to get the dissipation right, we would need a very small time step indeed. So let's say that we want to run the simulation in time at least 4 times, so that Kolmogorov vortex spins around 4 times, or about 4 periods. And then we'll resolve that by delta t, this time step. The time step, I know if I plug in just what the Kolmogorov time length is, it's L by the RMS velocity. I then would need to insert the Courant stability criterion. Just to remind you what that is, it says that my smallest length scale has to scale with the RMS and the grid spacing. So I can't have a phenomena jump over a cell, right? If the characteristic velocity is u, then I have to take a time step so that u can't, that phenomena can't jump over an entire computational cell in one time step. So delta t then is something like 1/2 delta x divided by the characteristic velocity. So I put these two together, this, and I get 8 times the large-scale characteristic length divided by the grid spacing, which we said will be the Kolmogorov grid spacing. So I can put in the Kolmogorov length scale in terms of the viscosity and the dissipation, and then I can put in the dissipation in terms of the large length scales and the characteristic velocity scales, and I see that the number of time steps I'm going to have to take to resolve just not even a full period of a vortex shedding, but just that small period of how fast that little Kolmogorov scale goes around would go like 10 times the Reynolds number to the 3/4 power. So together with my n cubed, that's my spatial resolution, times my temporal resolution requirement, if I plug these in, I see that my total number of flops or floating point operations goes like 10 to the 7th Reynolds number cubed. And I threw in here a 10 to the 3rd. That's the number of operations per time step. So when we discretize our domain and we're taking a CFD calculation, you might say for every time step there's 1,000 floating point operations. That's quite a conservative estimate. So it's akin to how many additions and subtractions do you need to do a 4th order Runge-Kutta, right? So if you go and look at all of those additions and subtractions within something like a 4th order Runge-Kutta, there might be 1,000 of those. And so we get this floating point operations goes like 10 to the 7th Reynolds number cubed. All right, so here's an example from 1997. This comes out of a very famous book by Stephen Pope on turbulence. This is for flow over the backward-facing step, and they used this super awesome Cray computer that could do 5.2 gigaflops. This was like the premier computer when I was in graduate school in 1997. The Reynolds number is quite modest, 5,100. And so they used, this is their grid size. This is the total number of nodes n. This is the total number of time steps they took, times 10 to the 5. And they used this Cray computer, which could give them 5.2 gigaflops per second. And they said that it took 54 days to do this calculation. 54 days to do one calculation on this small little domain such that you could resolve the turbulence. All right, so our estimate, let's just check it. Here's what we had for our estimate, and I'm going to lower that estimate just a wee bit. I'm going to increase the grid size to match what they did. They didn't go all the way down to the Kolmogorov scale. They went to 2 times the Kolmogorov scale, which is common in these DNS. They kind of cut corners just a wee bit. And you can see that it really manifests itself by 2 orders of magnitude. It went from 10 to the 7th to 10 to the 5th. So according to this scale length, this would be, here's my Reynolds number cubed, and then multiplied times 10 to the 5th. I get something like 10 to the 16th flops are required to do this simulation. And if I convert this to days, well, at first I divide by my computational resource. This computer 5.2 gigaflops per second divided by hours gets me to 708 hours or 28 days. So it's a good approximation. It's within a factor of 2 of, it's conservative, of what it actually took. So this is the actual simulation, and my Reynolds number scaling says it should take about 29 days. So it's a little bit off, but it's in the ballpark. It's impressive, right? It's an impressive resource. You know, if we were to do this calculation today on my desktop here, using my Mac Pro, which cost $4,000, right? What did this thing cost? $30 million for 5.2 gigaflops. I can get 3 teraflops. That's 3 orders of magnitude faster today in 2016 for $4,000. That's a mind-boggling increase. And remember, that's just Moore's Law here, right? So that's the sort of payoff you get for Moore's Law. Just a mind-boggling increase in power for cost. If I were to run that simulation today, it says it would take about 2.25 hours. That's unbelievable, right? 54 days from when I was in grad school to today. But this is an inconvenient truth, right? This is a simple calculation. And if I believe Moore's Law, and I just think this line here, the fastest computer in the world is going to go on forever, my notebook is going to continue to increase forever, irrespective of some quantum barrier that we're going to have to get over. Let's just believe Moore's Law lasts forever. What would it take to do a larger problem? Something we might actually be interested in, like a Reynolds number of 10 to the 6th. That's regular old flow down a pipe is about 10 to the 6th, turbulent flow. Or what about an airplane in flight, 10 to the 10th? What sort of computational resource would I need for that problem? So again, let's use this 10 to the 7th Reynolds number cubed. If I go 10 to the 7th times 10 to the 10th, which is my Reynolds number of flow over a jet airplane, that's 10 to the 37th. Wow. To solve this in an hour, so to be reasonable, there's this other theory out there that you can't do calculations in 28 days. No one has the mental capacity to wait 50 days to do a design problem, right? What are you going to tell your boss? Oh, I just launched this simulation for flow over an airplane. Give me 50 days. I'll be back in 2 months to make an assessment. And invariably, you put in the wrong number for the initial condition, so you got to wait another 50 days. So we can't wait 50 days. We need, if we're going to do design work where we're resolving the turbulence scale all the way down to the Kolmogorov scale, we need things in an hour or less, right? There's this law that says 15 minutes is actually a more reasonable sort of estimate. But let's go for an hour. If I want to solve this flow field in an hour, I'm going to need 2.8 times 10 to the 33rd flops. I'm going to need a computer that big. Here we are. Here's Moore's Law. Right now we're at exta. That's where we are in 2016. That's the fastest computer in the world. That's not like I got that on my desktop or anything. How long will I have to wait till the fastest computer in the world can do this in an hour? That's the difference between 33 and 18 is 15, right? Moore's Law says every 4 years we get an order of magnitude increase. So 15 divided or times 4, that's 60 years. I will be dead in 60 years. So I'll never see the realization of this, even if we can get there, right? Because people are thinking that in 2025 or so, there's the quantum barrier. And this is using the largest computer in the world. It's not like I'm going to have access to that. What if I need my desktop to do that, right? So my desktop is currently, the fast desktops are around 10 to the 12th. That's 84 years. You guys will all be dead in 84 years. So we'll all be gone by the time this comes to any kind of realization. Not too depressing, right? I think it's kind of cool. So we're going to need some way to do this today, right? We're going to need some way to do turbulence modeling, not DNS, but for design work to do many iterations of a design. We can't rely on DNS. DNS is great for research if you're doing one problem and a simple problem, a canonical problem, but not for design work. So we'll talk about that next time. Till then, I'll see you later.